Okay, now we have not addressed the original problem, and the original problem is how do I get a nice creative pattern? Let me just kind of flash it up there for you again. How do I get a nice regular kind of design that's different? It's not something you'd find all the time in bathrooms around, but yet it's something that's doable. And using regular polygons is going to help make that doable because all the sides will be the same length. I don't have to worry about these kind of things. And also, I want designs that repeat. I want things that happen all the time. I don't want to have to change different designs as I go around. So let me flash up. These are the usual kind of things that you see. These are what are called regular tessellations. And that means that, yes, they do use regular polygons to kind of cover a flat surface, but also they use the same polygon. You know, here I've got 4 squares around a point each time. And here I've got 3 hexagons around a point, 120, 120, 120. And then I've got 6 triangles around a point each time. So those are called regular tessellations. And the thing I want to point out about this is the distance, or not the distance, but the sum of the angles around each vertex, around each corner, is 360 degrees. And so that's my goal. Can I find a mixture of regular polygons whose angles add up to 360 degrees? Okay. Now, there's my formula for calculating the angles of regular insided polygons. I do have some limitations, okay? The number of sides obviously has to be more than 3. We talked about that. And it has to be a whole number. That's important as well. The measure of the angles. Well, a 3-sided, and I showed you this just a second ago, a 3-sided regular polygon, a triangle, has sides 60 degrees. So that's the lower bound on the measure of the angles. The upper bound, well, if you look at that formula, I've got n minus 2 over n. I'm putting in positive numbers. So that number, whatever it is a fraction less than 1. And then when I multiply both sides of that by 180, that means that the upper bound on that angle would be 180 degrees. So I cannot have an angle in these polygons bigger than 180 degrees. And then lastly, how many polygons can I put around a point? Well, because the angle measures are less than 180, I have to have at least 3. And because the smallest angle is 60, if you take 360 and divide by 60, you get 6. So there is a limitation to the number, different types of combinations I can have around a point. I've got between 3 inclusive, 3 and 6 polygons around a point. So it turns out there are a finite number of ways to do this. And you can find them systematically. You can start with 3 polygon sets and then work up to 4, then 5, then 6. And I'll show you the start of this. I don't want to do the whole thing, but I'll show you how to do this. And it actually helps if you know the inverse of the angle formula. The angle, I'm using a theta here. So it looks like a 0, but it's a theta. It's a Greek symbol. The angle is equal to this formula, right? So you can go through and you can solve for n. That gives you the inverse formula. If you know the angle, then you can find the n. It's just a little bit of algebra. You would clear it to fractions by multiplying through by n. And then we're going to solve for n, so I got to get all my n business to the other side of the equation, right? And then you factor out the n. And then if you don't like, I don't like negatives here, so you could multiply through by a negative. That changes the order and gets rid of it here. And then just divide by the junk. So you've got a nice little formula here. Once you know the angle that's left, this will tell you how many sides you have to have, the n. So we'll just use that little formula. Okay? So let's start with 3 polygons. Let's do it systematically and kind of show you how you would kind of go about this. I would start with 3 and then 7. Now, why not 3 and 3? Well, the first 2 have to add up to more than 180, right? The third one has to be less than 180. So the smallest number of sides I could use would be 7. And I go through and I calculate, okay, this is the measure for the equilateral triangle. This is for the heptagon. And so I'm left with an angle of 171 3/7 degrees, which sounds ridiculous. But if you plug that into the formula, that gives you a whole number, 42 sided polygon. You could do that. It looks like a circle, really, because the angle is so shallow. But you could do that. So there's one combination. If I go with 3 and 8, I'm just letting the second polygon get bigger. It works out to where I could use a 24-sided polygon. A triangle and a 9-sided would give me an 18-sided polygon. 3 and 10 gives me a 15-sided polygon. 3 and 11, okay, this is kind of weird. 60 is the angle in the triangle. This is the angle in an 11-sided polygon. It gives me this left, and when you plug that in formula, you get 13.5. Well, I cannot have a 13.5-sided polygon, so I got to bounce that one. That's not going to work at all. But you can just keep running through these. 3, 12, and 12 will work. And then once, I'm taking these in order, increasing order. So once I get to 3, 12, 12, I'm done with the 3s. And then I would move on to the 4s. So what I've done is I've actually run through all of them. I'll just list them for you. It's not worth going. You know the process now, so you can do it. You start with the 4s and you pick up a few more. Go to the 5s and you have actually 1. And then go to the 6s. That's the one I showed you, the 3 hexagons. Then you go to 4-sided things. You can find this one. And now with 4 things, the order they appear matters. So you can split up the 3s by putting the 4 in between them. Okay? And then 3, 3, 6, 6, you can split up the 3s and 6s by intermingling those. 3, 4, 4, 6, and you can split up the 4s by intermingling those. And then the last one there, and then you can look at the 5s and 6s. The real question is, these are ways to get them to add up to 360 degrees. The question is, can these things be applied through the plane repeatedly? Just because they add up to 360 degrees, is that all that I need? Okay? The way to kind of answer this is really to cut your patterns out and try this, but I can show you that it won't work in all cases. It will work in some obvious cases. The ones here where they're all the same, those are the regular tessellations I showed you earlier. Okay? Some will work, some will not. The 488 will work. Here's a square with 2 octagons, and I want this same pattern at each corner. Well, I can extend that, and I think that's pretty obvious that you can extend that. Just keep doing that, and you've got the same mixture of polygons at every corner. However, something like 5, 5, 10, here's a polygon and a 10-sided polygon. Okay, it'd have to be 5, 5, 10 here, and it has to be 5, 5, 10 here and there, but you see, at that blue point, you do not have enough space left. You do not have enough space left to put in another polygon. In fact, you don't have the pattern you need. You've got 5, 5, 5. Okay? So, some of these will work, some of them won't. And I think what I'll do is I will simply show you, rather than go through this exercise with all of them, I'll show you the ones that do work. Okay? The 3, 12, and 12 work. Although, and so does the 4, 6, and 12. These are some nice, cool patterns. I have to say that these would look neat on a wall or a tile floor or something like that. Although, good luck finding a 12-sided tile, regular polygon tile. That might be something that could be special made, but you may have trouble finding that at Home Depot or Lowe's or something like that. 488, I showed you it would tessellate, and I've actually seen this. This is one, I think octagonal tiles are something that you could find at the store pretty easily. And you could perhaps mix it up with some colors, do the squares a different color than the octagons. 3, 6, 3, 6, if you'll notice here, this is very linear. You see a lot of lines through here, but you have triangle, hexagon, triangle, hexagon at each point. Triangle, hexagon, triangle, hexagon, triangle. That happens at every point. You could perhaps mix that up with some different color tiles. These are the really cool ones. 3, 4, 6, 4. If you'll notice, you get these almost circular shapes. And let me convince you that this is really going on at each point. 3, 4, 6, 4. And then we go to a different point. 3, 4, 6, 4. 3, 4, 6, 4. It happens at every point. You could really do something cool with this. I think this would be a neat tile floor. And then also the 3, 3, 3, 3, 6 could be put together as well. These are called semi-regular tessellations. And by that, we're using regular polygons, so we keep the word regular. But it's we say semi-regular to mean that it's not entirely one polygon. We're using different types of polygons to tile the plane. There's a lot of other things you can do if you abandon this business of using polygons. And maybe we'll get a chance to talk about that, but you can do some cool Escher things where you start with a polygon, you remove stuff from one side and tack it on to the other side. And those kind of things, when you do that, they'll still fit together. Okay. I guess what I'd like to do is just very quickly, I'll give you some slides here, some summary slides that show you then the different things that are possible. Oh, wait, whoa, I'm sorry, I've got a couple left. I forgot these. There's 8. I'm sorry. Scratch the summary thing. Let me show you this real quick. I forgot these even were there. This is the coolest of the cool right here. The 33344 is okay, but it's very linear. That was my bad. I forgot these were even there. It's very linear, so I don't know if you like that or not. The 33434, this is bad. 33434, and that happens at every point. 334, where did my pointer go? 33434. That would be a really interesting design. Okay. So I guess what I'll do in closing is, and you can doctor these up with any kind of colors you want. What I'd like to do is kind of leave you with these patterns. You can always go back and review these and look at them, but very quickly I'll flash up some summary slides that show you the different kind of regular tessellations and then also the semi-regular tessellations that we talked about.